So this is going to be the first lecture, lecture 1, and this video will be part 1 on solution properties and also on solution and solubilities. All right, so we're going to talk about what is a solute versus a solvent versus a solution. Although they all start with S, they are different things. Then we're going to talk about some common vocabulary and definitions. These make great multiple choice questions on exams. And then we're going to talk about factors that affect solubility, like polarity and size, and resulting trends as a result of these factors. So, first and foremost, a solution is made up of a solute and a solvent. The solute is the substance dissolved in the solvent, and the component is the smaller amount. Okay, the solvent dissolves the solute. Okay, often is a liquid, doesn't have to be, and it is the larger amount or the larger component. Okay, and so we say things are miscible when they dissolve in each other in all proportions and nothing precipitates out or bubbles out. Okay, so really if you have a solution, okay, and we like to use water and NaCl because we've all seen water and salts. So let's say you have 100 grams of water and 5 grams of NaCl. Okay, what we call the water is the solvent. It is the larger component. NaCl is your solute. It is the smaller component. And the entire thing, when mixed together, is the solution. And it makes a huge difference what is the solution versus the solvent. Okay? And we have things in water does not have to always be the solvent. For example, if you have 300 mils of ethanol, okay, and you have 100 mils of water. In this particular case, the water is going to be your solute because it is the smaller amount, and your ethanol will be your solvent. And all together, when mixed together, you have a solution of ethanol in water. Okay? So, when we're describing a solution, oftentimes we'll talk about if it's saturated or unsaturated. A saturated solution, this is this word here, okay, is in equilibrium with respect to the given substance. Because it is in equilibrium, no more solute can dissolve. If you add more solute, it will precipitate. Okay, an unsaturated solution is not in equilibrium. Because it is not in equilibrium with the substance that is dissolved, then more solute can dissolve. So if you add more solute, it will dissolve and not precipitate. Okay, solubility is a term that we use to describe the amount of solute which will dissolve in a set volume. Okay, so like let's say if you look at this example here, if you take 30 grams of NaCl and put it in 100 mils of water, everything is dissolved. Okay, there's no solid. Okay, because of that, it is what we call an unsaturated solution. Okay, now if you take 40 grams of NaCl and add it to 100 mils of water, same amount of water, then you notice that all of it will dissolve except for a little bit which will precipitate out. In fact, 4 grams of NaCl will precipitate out. That means that only 36 grams has actually dissolved, 4 grams is precipitated, so the solubility is 36 grams of NaCl in 100 mils of water. Okay, so the solubility will tell you how much will dissolve in a given volume. Okay, it's really useful if you're making a solution, right? When a saturated solution is pulled something like this up, and it's really easy to make the correct amount of solute in the water. A supersaturated solution has more dissolved solute than the saturated solution, and often it is done by preparing a saturated solution at a higher temperature, and then we cool the solution down, and it makes a supersaturated solution. Now, the idea of miscibility, or when things will mix together without anything precipitating out, is determined by a rule like dissolves like. This means that similar substances dissolve one another In particular, we're talking about polarity. So if you have a polar compound, it will dissolve in a polar solvent or solution, and a nonpolar compound will dissolve in a nonpolar solution. Okay, we know, for example, sugar is C6H12O6. Because of all the oxygens, it makes it very polar. Okay, and we know that water, which is H2O, is also very polar. So sugar dissolves in water, and we know this for a fact. Otherwise, we couldn't have all our sugary drinks that we like to drink. Nonpolar compounds dissolve in nonpolar solutions, and spices are nonpolar. Okay, a lot of the aromatic smells like cinnamon and garlic and these kind of aromatic spices that we like to use in cooking, they are the particular aromaticity of the spices is due to nonpolar compounds. Okay, that's why when we often start cooking something, we take the spices like the garlic and the cinnamon and others. I can't think of any other spices right now, but we cook it in the oil, right? And then all that flavor goes into the oil. Why does the flavor go into the oil? Well, is because the oil is nonpolar and the spices are nonpolar, and so they mix well together. So then you get an oil that is really aromatic in that particular spice. So polarity is an idea that is relative. So for example, if you have acetone is carbon double bonded to oxygen with hydrogens on each side. Okay. How would you classify if this is polar or nonpolar? Well, let's look. You have this end here, which is carbon and hydrogen, and this end here, which is carbon and oxygen. As you know, the difference in electronegativity between carbon and oxygen is quite large. So this is a polar fragment, whereas carbon and hydrogen, the difference in electronegativity is quite small. So it is nonpolar. Okay, let's compare it to something like water. Okay, water is bent. Hopefully we remember that from our Vesper chapter in 151. Okay, so really oxygen is partially negative, hydrogen is partially positive due to the unequal sharing of electrons, and so it is what we call a very polar species. Okay. Last but not least, we have something called hexanes. Hex means 6. So really it's 6 carbons linked together. Okay. And on each carbon there are hydrogens. Because of all these carbon and hydrogens, this is what we call a it is hexane, but it is called a hydrocarbon. Okay, and this word hydrocarbon is very important because hydrocarbons are always non-polar. Again, due to the difference in electronegativity between carbon and hydrogen. Okay, so really, we say hexane is non-polar, water is polar, acetone is a mix, right? It is non-polar and it is polar. It is more polar than hexane, okay, say like this, okay, but it is less polar than water because of its hydrocarbon piece, the C and the H portion, okay. So oftentimes we like to be able to put compounds in terms of increasing polarity or increasing non-polarness depending on what we're looking at, okay. The reason for the like dissolves like, okay, is because of the attraction between similar species. For example, a nonpolar species is very much attracted to a nonpolar species, whereas a polar species is very attracted to a polar species. So let's look at an example, okay? Let's say that this is water, okay, and this is methanol, okay? Because this is got the OH groups, okay? Both of these are very polar, okay? So there's an attraction there between the two compounds, right? So if we look at these two, they will be miscible. Why? Because there is an attraction between the orange and the blue balls, because like like and like attract each other, right? Really, it's a competition between is this attraction greater or is this attraction greater, right? If this attraction is greater, then things will be not miscible. Okay? If this attraction is greater, then things will be miscible. Okay? Now, if you have water and methanol, it is miscible. But what if, for example, you have water, and instead of this, you have something like CH4? Okay? Remember, it's a hydrocarbon, so now it's nonpolar. Okay? Now, this attraction between the orange and the blue balls is going to be very small because polar and nonpolar are not attracted. And so you would assume that these two things are going to be not miscible. Okay? Now, when we're looking at molecules, often like we did with acetone, we would like to break it apart and look at each part and see what it is in terms of its polar or nonpolar portions. So, for example, if you have something like methanol, you have a polar portion and a hydrocarbon nonpolar portion, right? Okay. You would think that methanol is fairly polar because the hydrocarbon portion is very small, right? This part is very small. Okay, and look, it's very miscible in terms of water. Okay, polar and water is polar, right? So like dissolves like, no problem, it is miscible. Okay, but let's look at the last compound here on this table. It has a large CH portion, so it is got a large hydrocarbon fragment. Okay, and the polar part is very, very small, right? In comparison, okay? Because of this, this is going to be nonpolar because of the hydrocarbon. And so with water, it is very not miscible, okay? 0.6 grams will dissolve in 100 grams of water. That is very, very little, okay? And again, it has to do with the water being attracted to the so there's the oxygen and the hydrogen. There are what we call hydrogen bonding between the hydrogen and the oxygens in the molecules. So a lot of times for things like exam problems and homework problems, we like to kind of rank what is soluble and kind of predict the solubility. So in that first question, they're asking you benzene. Is it more soluble in methanol or pentane? Okay, so benzene is a carbon ring. It's got 6 carbons in it. Okay, they're double bonds every other carbon, and it's covered with hydrogens. So this is benzene. Okay. In comparison, CH3OH and pentane, pent is 5, right? So there are 5 carbons. 1, 2, 3, 4, 5 carbons. Okay? And of course, a bunch of hydrogens. Okay? In this particular case, you would say that both benzene and pentane are what we call hydrocarbons or nonpolar species. Okay, so you would predict that like dissolves like. So benzene and pentane are going to be soluble or miscible. Okay, the problem with the methanol is the OH group making it very polar, so it is not soluble in the pentane or the benzene. Okay, another kind of problem is they're asking you to arrange the following substances in order of increasing. So we're going to do increasing solubility in pentane. So if we're comparing it to pentane, pentane is nonpolar. Remember, pentane here is nonpolar hydrocarbon. So this increasing solubility, so the most soluble will be something that is nonpolar. Okay, so out of water and propanol and the species here, you would say the most nonpolar is this one, right? It's got the largest hydrocarbon, 3 carbons, right? And it only has 1 OH. So the most nonpolar is going to be here. Your most polar, i.e. least soluble, is going to be the water, has no hydrocarbon, and in the middle is your compound with just 2 hydrocarbons and 2 OH groups. Okay, you should be able to do this on homework, which you will have to do. Another factor that affects solubility is the idea of ion dipole interactions. Okay, so if you're looking at how things are solubilized, you have some solid here. Let's call this NaCl. Okay, here. Sorry, this should be NaCl, Na plus Cl minus. So your Na is going to be your positive cation. Remember, cations are positive. Your negative is going to be your Cl minus. It's your anion. Okay, really there is a lattice energy attraction here, right? Between your positive and your negative charge, right? This kind of attraction here is called a lattice energy. Okay, so for something to dissolve in water, water will need to come in and break apart the lattice energy and form a new kind of attraction. This kind of attraction, where the water surrounds the cation and anion, is called an ion dipole interaction. The reason being, you have an ion here, you have a dipole for the water due to the partially negative and partially positive ends. And so there's an attraction there between the cation and the anion and the water. So it's called an ion dipole interaction. Okay, so really the question is the lattice energy greater or the ion dipole attraction greater? Okay, and that's what we see here going on this side. If you have something like water, remember it is partially negative, so there's a partially positive end. So you have an ion and you have your dipole. Okay, and there is an attraction there. Okay, whereas you have the lattice energy between the cation and the anion, so that is the attractiveness between the positive and negative charge. Okay, if the ion dipole interaction is greater, it is called the hydration energy. And the hydration energy, if it is greater than the lattice energy, it's going to make the solid soluble. If it is smaller, then it is insoluble. That is the reason why certain salts like NaCl, 36 grams can dissolve in 100 mils of water. Why? Because the hydration energy is greater than the lattice energy. Okay? Whereas something like calcium phosphate, only 0.002 grams will dissolve because the hydration energy is smaller than the lattice energy. Okay, so what determines the hydration energy and the lattice energy? What factors affect that? 3 factors, 3 main factors. The magnitude of the charge is the first factor. When we talk about magnitude of charge, we're looking at this and saying what is the numerical value, what is greater. Okay, when this charge is greater, there is a greater lattice energy. It makes sense because 3 minus is going to attract much more positive charge than, say, 1 minus, right? So the larger the charge, the greater the magnitude of charge, the greater the lattice energy. So here you can, let's go back here. If you have Ca3PO4 versus NaCl, right? Remember that this is miscible. Okay. Why is this not miscible? Because this has a PO4 3- charge. So the lattice energy is high. Okay. The lattice energy is also inversely proportional to the distance between the ions. So for example, if you have Mg, which is small, and Ba, which is big, okay, the charge is the same, but because Mg is small, the distance between the ions is small, so therefore the lattice energy is large. We read that better. Larger lattice energy. Okay, because this is small. Okay, whereas barium, which is big, will have the smallest lattice energy. Okay, the smaller the ion, the higher the hydration energy. So again, this is the smallest, so it will have the smallest hydration energy. Okay, and the barium is the largest, so it will have the largest hydration energy. Sorry, I've mixed that up. It's the smaller it is. Sorry about that. The smaller it is, the higher the hydration energy. So it will have the largest and the smallest. Sorry, I've mixed that all up. Okay. So, really with all of these things, the best thing to do is to look at each one of these factors, the magnitude of charge, the size, and kind of decide which it has, the higher or larger hydration energy. Now, temperature often will affect solubility as well. Most salts, the higher the temperature, the more soluble it is. Gases are different. Gases are less soluble at higher temperatures, but with ionic compounds, usually, it's like potassium nitrate. As you increase the temperature, you increase the solubility. However, there are certain things like cerium selenate where you have an increase in temperature and it actually decreases in solubility. Okay, and really this is an idea of something exothermic versus endothermic when it comes to salts dissolving in water. And it's actually used for ice packs and hot packs. For example, if you have calcium chloride, when you dissolve it in water, it's exothermic. And so it's great for things like making hot packs, whereas if you have ammonium nitrate, it actually absorbs energy, is endothermic, and therefore makes great cold packs. So what you have is a cold pack. You have some salt and you have water surrounding it. They're separated usually, and then when you crack it and break it apart and pound on it, it will dissolve the salt into the water, and so it will be a cold pack if it's endothermic process, and it will be a hot pack if it's an exothermic process. It's actually quite fun to play with. Last but not least, you have solubility in terms of pressure. The solubility of gases are also affected by pressure according to Le Chatelier's principle. We'll talk more about this in a later chapter, but for now, all you really need to know is that when you increase the pressure, you obviously increase the solubility. So if you have a gas here, if you press down on this piston, it will actually increase the pressure. When you do that, obviously what will happen is more solute will dissolve, and so you're basically increasing the solubility. Okay, this is basically represented by Henry's law here, where your S is the solubility and P is the pressure. So as you increase the pressure, you will increase the solubility. Okay, that's the end of lecture 1, part 1. Go ahead and watch this video all the way through, and then do the corresponding homework in the homework booklet, and then you can go ahead and watch the next video in this module. So this is the end of lecture 1, part 1.